Hey everybody, Dr. A here, and in this video we're going to be providing some background information on the method of joints for trusses. So let's go ahead and get started. In order to determine the member forces of a truss structure, we can use one of two methods. In fact, we could use both methods in tandem, which we'll talk about in a later video. But those two methods are method of joints, which we abbreviate MOJ, and the other method is method of sections, which we abbreviate MOS. Now, MOJ is more applicable when we want to compute all the member forces in a truss system. So if you have a problem or a situation where you're asked to calculate all the member forces in a given truss, you're probably going to want to use method of joints. Now, method of sections, which we're going to talk more about in another video, is more applicable when you have a large truss system and you only want to compute some of the member forces. So let's say you have a really big, complicated truss with several members, and a problem asks you, oh, I just want the forces in these three members in the middle of this gigantic truss. Well, method of sections would probably be more applicable in that kind of situation compared to method of joints, but you can use these two methods together if you needed to. Okay, so in this video, we're going to focus on the procedure for method of joints, and then we're going to have some examples, and then we're going to have another video with some examples of method of sections. So how do we apply method of joints? What is this procedure? Well, the first thing we are going to do, I'm going to say number one, we're going to say begin MOJ analysis at a joint having at least one known force and at most two unknown forces. Okay, so let's underline that. That's a really important sentence. We always start MOJ analysis for a truss at a joint having at least one known force and at most two unknown forces. Okay, so you got to start at a joint where you know something, and you also, that joint has to have at most two things you don't know. Now, the reason for that, especially for the second part of that sentence, the second phrase there, the reason for that is really number two in the procedure. So what we do is we apply particle equilibrium equations to each truss joint. Now remind me, what are particle equilibrium equations? Well, that's sum of the forces in the x direction equals 0 and sum of the forces in the y direction equals 0. We apply that at each truss. So we've each truss joint. So we've seen this before, right? We've dealt with particle equilibrium in this playlist or this course before. So we're not doing anything really new here. Okay, so what about external support reactions? Okay, I'm going to make a note here. Okay, I'm going to say note. We may or may not need to solve for external support reactions on the entire truss first. Okay, what does that mean? Well, remember, your truss is still going to be supported by some external supports. Now, depending on the geometry of the truss itself, you may or may not need to get those external support reactions first. So let's look at an illustration. If we have what we would call a 3-bar truss, So we have these three members here, and let's say that down here we have a support, a pin, and a roller. And let's say this is joint A, B, and C. And let's say we have a force F at A. So how would we begin our method of joint analysis for this type of illustration? Well, we look at number one, begin the analysis at a joint having at least one known force and at most two unknown forces. So joint A has one known force. Guess what it is? That's that applied force F, and two unknown forces. What are the two unknown forces? Well, that would be the force in AB and the force in AC. Okay? How do I know that? Well, if I look at a free body diagram of A, if I peel out joint A by itself, what do I have here? I've got that known force F, that's like an applied force. And then I've got FAB. Oh, let me change colors and be consistent with my color coding. I've got FAB and I've got FAC here. So these member forces are the unknown forces, right? I mean, that's what you're trying to find. You're trying to find what the member forces are. So you would start in this illustration at joint A. Now, what will we do next? Well, again, we're applying principles of particle equilibrium. So after we calculate FAB and FAC, we are then gonna do what? We're gonna move to, excuse me, I got a little cough. We're gonna move to one of the other two joints that also satisfies number one here, okay? So watch this. If I'm done with A, the next one I'm going to move to is joint C, okay? Now, what's happening at C? Well, at C, we now will have, after analyzing A, we will have one known force at C, and that'll be FAC, okay? So if we look at a free body diagram of C, guess what we're going to have? We're going to have that known force, FAC, and what are the unknowns going to be? The unknowns are going to be, for example, CY and FBC, okay? So once again, order matters. Order matters, all right? Let's say you tried to start with joint C at the very beginning. If you tried to start at joint C before tackling joint A, you're going to get stuck immediately, because starting at joint C from the very beginning, you have three unknowns, right? You've got CY, FBC, and FAC. So none of these three would be known to you if you attempted to start at joint C, okay? Which is why we started at joint A, because joint A, again, had the one known force, which was this applied F, and the two unknowns, which are the two member forces, okay? What about joint B? What if I had tried to start at joint B first? How many unknowns do we have at joint B at the very beginning? Well, at the very beginning, you have four unknowns at joint B, right? Because at the very beginning, you don't know FAB, you also don't know FBC, you also don't know BY or BX, okay? So that's why we always have to remember number one here, always identify the joint where you have something you know and at most two things you don't know. Start there and then move to the next joint over that still satisfies that number one, okay? Now, let's talk about sign convention, okay? And again, we're still kind of under the procedure here. All right, let's talk about, we're going to call this, I guess, bullet point number 3. Bullet point number 3 is the sign convention, okay? So for the sign convention, what we typically do is we assume the unknown member forces act away from the joint, okay? Now what this is doing is this is assuming tension in the member, okay? Now what happens is when applying equilibrium equations, if a member force is computed as negative, then the force is pointing in the opposite direction and is in compression. Okay, so we've got to start by our analysis with some kind of assumption. Right now, if you notice in my little figures here, I drew these unknown forces pointing away from the joint, okay? Pointing away from the joint indicates that that particular member is experiencing tension. So we start with that assumption. We apply those equilibrium equations per step 2. And if something comes out as negative, what it really means is that particular force is pointing in the opposite direction of what we assumed, which really means that member is in compression, okay? Now, as we do some numerical examples, we're going to see this in action. We're going to see examples and illustrations of this, but these are the basic 3 parts of the process for executing method of joints. And again, it's really just a type of particle equilibrium analysis, jumping from joint to joint. And remember, we may or may not need to solve for externals first. We might remember from a previous video, the truss as a whole is a 2D rigid body, but each joint is a particle, okay? So the entire truss is a rigid body, but joint by joint, you're doing particle equilibrium analysis. All right, so that concludes this video. If you found this helpful, please hit like and subscribe, and be on the lookout for the next few videos, which have some examples of us illustrating this. Thanks for watching.